Singapore stands out as one of the most remarkable nations in Asia in terms of economic growth and public infrastructure development. Although Singapore is a small city-state, it has gradually developed into a major hub for international trade and transshipment since becoming a free port in the 19th century. With a population of just 2.5 million, it once recorded as many as 10 million tourist arrivals in a single year. In order to uphold Singapore's national image, every aspect of its development not only emphasizes harmony and aesthetics, but also demonstrates an impressive standard of engineering quality. Singapore's transportation infrastructure is renowned for its speed and aesthetic appeal. To address urban traffic congestion, the government has imposed various restrictions on private vehicles, while developing a public mass transit system tailored to the needs of its citizens, making it an indispensable part of daily life. Singapore's mass rapid transit system serves as the island's primary transportation backbone, fast, efficient, and with balanced capacity. Influenced by Western culture, both its engineering management and operations adhere to global international standards. When it comes to quality control, the standards are exceptionally rigorous and meticulously enforced. After years of development and effort in Singapore, RETSAIR Engineering Agency's overseas engineering personnel also took part in the MRT system project. As the only Chinese team involved, their achievements in both management and quality earned praise from the Singaporean government. RETSAIR Engineering Agency's Singapore office participated in the bidding process for the MRT system project organized by the MRT Corporation a total of 9 times. While the first 8 tenders were unsuccessful due to pricing and financing terms, Contract 405 was the 9th attempt. After numerous meetings between both parties to clarify the tender documents and financial terms, and more than 100 written questions and responses exchanged, it was finally decided on January 6, 1986, that the project would be awarded to RETSAIR Engineering Agency. This project was undertaken through a joint bid between RETSAIR Engineering Agency and the local company Hock Lien Sang. A 45-day mobilization plan was immediately drawn up, and the mobilization process commenced under computerized control. Construction of Singapore's mass rapid transit system began in 1983, comprising the North-South Line, East-West Line, and the Western Branch Line. Contract 405 covered the Western Branch Line, stretching 6.2 kilometers from Jurong to Bukit Panjang. It was a double-track route divided into sections A and B, constructed in sequence. Most of the alignment consisted of elevated structures, along with a 136-meter-long tunnel. The precast beams for the elevated viaducts were produced by RETSAIR Engineering Agency at 3 dedicated precast yards established specifically for the project. This section of the line includes 3 stations, each a modest structure standing 2 to 3 stories high. The stations were specially designed to blend with the surrounding environment and reflect the local cultural context. In consideration of the Singaporean government's emphasis on national image and its goal of attracting tourists, the architectural design and decorative appearance of these stations were made distinctively unique. From the outset, the project's mobilization plan was managed through computerized control, reflecting the stringent standards of its engineering management. According to regulations set by the MRT Corporation, the progress of construction was managed using the critical path method. This required the use of computers to generate detailed network diagrams and progress reports. Multiple subsidiary network charts essential to the construction process were stored in computer files, and each report clearly indicated the deadlines for every key milestone. Such progress control reports provided a clear overview of current objectives and upcoming tasks. Although most of the MRT Contract 405 project consisted of elevated viaducts and was not technically difficult in nature, the wide range of local government requirements and regulatory constraints made progress particularly challenging. In line with Singapore's policy on technology transfer, the majority of engineering personnel had to be locally hired, while the RETSAIR Engineering Agency staff who held primary responsibilities also had to allocate part of their time to train local personnel, in order to improve their technical skills. In addition, Under the Singaporean government's policies to protect the environment and enhance quality of life, contractors were required to minimize construction-related pollution, strengthen on-site safety, and improve traffic signage around work zones. As a result, this project demanded not only high standards of construction quality, but also strict attention to the surrounding environment in order to meet governmental expectations. The Pan Island Expressway serves as a vital transportation artery across Singapore. For the cast-in-place bridge segments along this route, temporary support structures were specifically designed to ensure both construction efficiency and traffic safety. These supports were independently designed by RETSAIR Engineering Agency's project engineers and underwent thorough review by the client's professional engineers and appointed consultants. Construction was permitted only after full compliance with all regulatory requirements had been confirmed. The 136-meter-long tunnel was constructed using the cut-and-cover method. But during the construction period, pollution control was required throughout the entire excavation and transportation process. And upon completion of the project, the ecological environment of the hillside had to be restored to exactly the same state as before construction began. With the dedicated efforts of all RETSAIR Engineering Agency personnel, after passing a series of strict evaluations and controls, the Mass Rapid Transit Corporation of Singapore was highly satisfied and awarded RETSAIR Engineering Agency a certificate of commendation and assigned Contract 405B to RETSAIR Engineering Agency ahead of schedule. Section B was located in a suburban area, completely different from the environment of Section A. For control point measurements and topographic surveys throughout the entire section, all survey data and topographic maps had to be reviewed and signed by a locally registered surveyor in Singapore before being submitted to the MRT Corporation for re-verification and approval. This shows that, apart from demanding progress, the local government also enforced strict supervision and evaluation over the engineering works. The construction of the elevated viaducts, being located between residential areas in the city, required every aspect of the construction design to be thoroughly considered and carried out with great caution. Before starting foundation work, detection equipment had to be used to identify the positions of all underground cables and utility lines, so that they could be relocated accordingly. Board piles served as the primary foundation supports, with a total of 1,775 piles, each 1 meter in diameter and ranging in length from 3.5 to 30 meters. Due to the complex geological conditions, comprising mixed soil layers and massive granite boulders, the construction process faced numerous challenges. To accelerate progress, up to 16 different types of piling rigs were deployed simultaneously, each achieving an average drilling rate of 8.2 meters per day. The client imposed particularly strict quality control over the board piles. Every process and material was supervised and inspected by assigned personnel. For steel pipe piles, sections A and B had a combined total of 252 piles, with an outer diameter of 65 centimeters and lengths ranging from 15 to 25 meters. In addition to the steel pipe piles, there were also 1,284 precast concrete piles, ranging in length from 6 to 25 meters. The quality of the foundation piles was controlled based on the results of test piles. The allowable settlement under the design load was not to exceed 9 millimeters. Under 1.5 times the allowable load, the settlement was not to exceed 20 millimeters. The maximum permanent settlement was limited to 5 millimeters. Many aspects of the project's design were made with structural safety in mind for the next century. For the foundation of the elevated viaduct, within an area 11 meters long and 8 meters wide, nearly 70 metric tons of reinforcing steel was embedded underground. From this, one can imagine how densely the rebar was arranged during construction. The steel formwork for the bridge columns underwent repeated inspections and measurements during finishing, with even the tiniest gaps filled with sealant to maintain the clean appearance of the column exterior. As for the tied rebar, even stricter attention to detail was required. Plastic bags were placed over the tops of the column rebar to prevent contamination from concrete, and after formwork removal, The finished columns were wrapped in plastic sheets to ensure uniform curing of the concrete. To ensure precise control during the fabrication of the cap beams, which were the most critical elements during construction, Retzair Engineering Agency specifically adopted steel frame supports, which provided better accuracy in measurement control and structural stability compared to the steel pipe scaffolding used by other contractors. The success of the cap beams depended heavily on precise surveying. To ensure accurate placement of the main girders, as many as 83 measurement points were installed on each small structure to control elevation, shape, and dimensions of the structural body. The tolerance limits were extremely strict, with all deviations measured in millimeters. During the assembly of formwork and the tying of rebar, repeated measurements were carried out to ensure that the future placement of the girders would be perfectly aligned. A total of 420 precast box girders were used for the elevated viaducts, each weighing between 80 and 165 metric tons. To minimize the impact on the surrounding environment and urban traffic during girder installation, the balanced cantilever method was specially adopted, minimizing the environmental impact to the lowest possible level. This approach exemplifies one of the key characteristics of urban engineering. In the process of suspended precast girder installation, the box girders were first fabricated at 3 precast yards. Once completed, they were lifted by yard cranes and moved to the storage bay. In the storage bay, finishing work was carried out in accordance with construction specifications. Then, the girders were lifted again by the precast yard crane and placed onto ground-level transport trolleys, which carried them to the lifting point of the overhead gantry crane. The gantry crane then lifted the girders and placed them onto a transport trolley positioned on the elevated viaduct. From there, the trolley transported the girder to the launching point at a speed of 2 km per hour. At that point, the precast girder itself acted as the launching beam, advancing toward the counterweight block on the next cap beam. The launching system was then pushed forward and fixed onto the following cap beam, at which point the girder installation could begin. Using the front hoist of the upper beam on the cantilever launcher, the precast girder was lifted from the front transport trolley and secured in place. The rear trolley then advanced the launcher forward. Once the girder reached its designated position, using the rear hoist, the girder was lifted off the trolley. In this way, by using both the front and rear hoists on the upper beam, the girder was continuously moved and placed onto the bearing pads on the cap beam. With this, the entire suspension process was considered complete. The fabrication of precast box girders at the precast yard was a highly complex process. The required dimensional precision was nearly equivalent to that of mechanical lathes. For a box girder measuring 22.3 meters in length, the allowable tolerance was only 5 millimeters. Therefore, from the initial inspection of the steel formwork to the placement of rebar and embedded components, it had to undergo repeated inspections by the client's supervisors and surveying personnel before production could continue. The MRT Corporation initially estimated that casting a single girder would take 17 days. However, through continuous experience and process improvement, Retzair Engineering Agency's personnel achieved a record of completing one girder in just 9 days, while maintaining excellent quality that earned praise from the client. Although the completed precast girders already featured smooth curves and well-defined contours, but according to the client's construction specifications, the final surface polishing had to achieve a smooth finish. After being placed onto a trolley equipped with diesel-powered generators, the precast girder was transported smoothly and quietly along the pre-laid tracks at a speed of 2 km per hour to the starting point of the launching system. Before this, the bearing pads on the cap beam, where the girder would be placed, had already been measured and aligned, and fixed in position using a rapid hardening agent. Their position was a critical factor in the suspension operation. Powered by the launching trolley, and using the precast girder itself as the launcher, the system was moved to the counterweight block on the next cap beam. Then, the 2 main support frames of the launcher were slowly pushed forward onto the next cap beam. Once the support frames were properly positioned and secured, the girder transport trolley moved forward, and using the hoist beneath the launcher frame, the precast girder was slowly placed onto the girder position. The maximum allowable placement deviation was 4 centimeters. Afterward, the reserved holes in the bearing pads were filled with rapid-setting grout. Within 4 to 6 hours, the grout reached the same strength as concrete, thus permanently fixing the girder in place. For this type of MRT elevated viaduct, the requirements for construction precision and surface smoothness far exceeded those of typical railway or highway bridges. The length tolerance for each precast girder had to be within 1/3000, and the allowable deviation in surface smoothness could not exceed 1/500. Achieving such technical standards required an exceptional level of care and endurance. To meet the requirements of quality control and scheduling, a special electromechanical coordination team was established to coordinate with the 11 electromechanical contractors under the MRT Corporation. When problems arose between civil and electromechanical work during construction, members of the team would work to resolve them, and were also responsible for preparing civil electromechanical construction drawings and work schedules. These schedules, along with equipment deployment plans, construction methods, and personnel arrangements had to be entered into the computer system and reviewed by the MRT Corporation before construction could proceed. Each day's completed progress was then sent back to the system for effective tracking, revision, and adjustment. In addition, the computer system was formally integrated into the project management information system, covering files related to cost estimation, personnel payroll, and equipment deployment. It was connected to the main server at the Retzair Engineering Agency headquarters in Taipei. In response to quality and scheduling issues or requests raised by the client, regular coordination meetings were held, along with the preparation of supporting project documentation to provide clarification. Through its participation in large-scale international construction projects abroad, Retzair Engineering Agency accumulated valuable experience and technical expertise, which it applied in Singapore through advanced engineering management and construction techniques, earning the recognition of the Singaporean government, long known for its strict standards. The consulting organization employed locally, along with American-style quality and progress management, under the collective effort of all Retzair Engineering Agency personnel, with a comprehensive plan, correct methods, and the united spirit of Retzair Engineering Agency, and in 1990, the project was completed on schedule and successfully fulfilled its mission. It once again stands as a model of success, both for the organization and for the nation.